class stuff. All right, so wanted to start this morning by just talking a little bit about 2 points that you might have missed yesterday in the packet, because they're not necessarily the clearest. One of them is in the box on the bottom of the second page, and one of them is in the box on the bottom of the first page. When you're using the law of cosines, and you're finding an angle, you want to find the biggest angle first. Okay? When you're using the law of sines, and you're finding an angle, you want to find the smallest angle first. Okay? Reason for that is because of the restrictions that come from the law of sines or cosines. Okay? Or I shouldn't say the restrictions from the law. Restrictions from the inverse cosine. So for cosine, remember we restricted cosine to the top half of the unit circle. So cosine will give you an angle, or inverse cosine I should say, will give you an angle between 0 and 180 degrees. So it will give you an obtuse angle. Okay? That's why law of cosines always find the biggest ones. For sine, that's restricted to the right half of the unit circle. So that's only going to give you an acute angle. So that's why we go smallest with law of sines first. Okay? Alright? Biggest law of cosines, smallest law of sines. With that now being said, what I would like you to do is I would like you to warm up with this particular problem. You seem to be shaking your head. What's the problem? So this is no triangle. Okay? Because what you're saying is that in a triangle, the 3 sides, the 2 short sides, have to be bigger than the longest side, right? Okay? Yep. So 1 plus 4 is not greater than 8. Okay? Love it. No triangle. Now, let's say you missed that. Okay? Which angle should we be solving for first in this one? We should be solving for angle C because angle C is the biggest angle. Biggest angle is opposite biggest side. Smallest angle is opposite smallest side. So if we were to have missed that, so then we would have used C squared equals A squared plus B squared minus 2AB cosine of C. And so we would have said here then that 8 squared equals 1 squared plus 4 squared minus 2 times 1 times 4 times the cosine of C. So 8 squared is 64, minus 1 is 63, minus 16 is 47, equals 2 times 1 times 4 is 8, so negative 8 cosine of C. And then I would have gotten 47 over negative 8 equals the cosine of C. And here, this value is not between 1 and negative 1. So if I would have gone to my calculator to do inverse cosine on something that's almost 6, I would have gotten domain error or dimension mismatch or error or one of those things. Pitchers and catchers reported a couple weeks ago. Spring training is in full effect now. So let's talk baseball. Okay. So the bases on a baseball diamond are 90 feet apart, and the front edge of the pitcher's rubber is 60.5 feet from the back corner of home plate. Find the distance from the center of the front edge of the pitcher's rubber to the far corner of first base. Then find the angle between the segments connecting the pitcher's rubber to first base and the pitcher's rubber to home plate. Okay. Those of us that are familiar with baseball, what shape are the four bases of the infield in? They're a square. Yep. It's diamond because it's on its side. It's tilted. Okay? But they are a square. So let me get out a square here. Oops, tap the brakes. Get rid of that one. Okay. I think I got it pretty close. Let me. Oop, nope. Off by a little bit. Oops. Why is it giving me that goofiness? There we go. Okay. So home plate is down here. Pitcher's rubber is right there. What else do we know? What you got, Rod?
The angle from like third base.
So all of these are 90, is what you're saying. Because that's where the bases are, yep. Okay. But yeah.
The distance from home plate to first place
Is 90 feet. Okay. So we know that this distance in here is 90. So kind of just fill that in. It says what? That is 60.5, yep. Okay. Yep. Yep. And from first to second. Okay. So all of these. Okay. Okay. But more importantly, this angle here is 45 degrees. That angle there is 45 degrees. This angle here is 45 degrees. And this angle here is 45 degrees. Right? Okay? Because now what we want to find is we want to find this distance right there. Right? Yep. Yep. So let me break out that triangle. We said that this was 90. We said this was 45 degrees. We said this was 60.5. And this was x. What can we use? Law of cosines. Okay, let's go. Go with law of cosine. And if we get an answer, if x is 60.5, then we know that it's a right triangle, right? But if x is anything but 60.5, it's not a right triangle. Okay? So find me x, please. I get 63.717 feet.
Doesn't matter how many decimal places put down.
We'll tell you on the test.
Okay.
I always go 3 because we got it. Because I also saw what's coming up,
Yeah.
and we got to use that. So I don't want to round it to tenths just yet. I actually left it on my calculator, just so you know. Go for now. 3. 3 is a good spot. Okay? So not a right triangle, right? So the second question that was asked was, then find the angle between the segments connecting the pitcher's rubber to first base, that's our orange X, and the pitcher's rubber to home plate, that's our blue 60.5. So we need to find this angle right there. Okay? How am I going to find that angle based off of what we have? Law of cosines? Or is it easier? Law of sines. Yeah. We'll on any triangle, you should only have to use law of cosines one time. Okay? Because then after that, we can use the law of sines. So if I go a little LOS here, I could say that the angle, the sine of angle P, I'm going to call it P because it's at the pitcher's rubber, over 90 is going to equal the sine of 45 degrees all over 63.717. Should have been in purple. Picked the wrong color. Okay. So angle P is going to be the inverse sine of what? What is angle P going to be the inverse sine of? Yep. I get angle P to be 87.176 degrees. Yes?
You want us around degrees as well to 3 decimal places?
I round everything to 3 decimal places. More decimal places, the closer I get to being exact. Okay. Building inspector Trinity checks a building in the shape of a regular hexagon. Regular hexagon has how many sides? 6. Each side is 40 feet long. She checks that Linz's construction located the corners of the foundation correctly by measuring several diagonals. Calculate what the measure of the 3 diagonals from one of the building's corners should be. Give you a couple of minutes to visualize, picture, solve. Good times.
Considering that this is equidistant, this is equidistant, would we say that? Huh? What are the 3 diagonals?
Right, so there's my regular hexagon. Agree? So if I lock in, we're standing at that corner, right? So then I've got this side or this diagonal right there. I've got this diagonal right there, and I've got this diagonal right there. Agree? Okay. So I know that each side is 40. What else do I know? Oops, I forgot this one's 42. What?
There's right triangles.
There is? Where?
Bottom right point to the top of the green line. And then over time. Yeah.
How? Think?
I think.
Think?
I don't know.
I'd rather know than think.
Because
What do we know? How do we come up with the interior angles are 120 degrees? So this is 120 degrees here.
Which means, since they're both 40,
Yep.
the two other angles are equal.
Yep.
So if you 180 minus 120, you get 60. So divide that by 2, you get 30.
So then that one's 30.
The other one's 30.
That one's 30.
Yep.
Which means
That you can that if you split that through the middle, it's like a right triangle.
so the red, purple, black triangle is a right triangle. That one.
Well, I guess yeah, but I was also saying to solve for the purple.
Okay, to solve for the purple.
I'm saying you can divide or split the triangle.
What can I use to get purple?
Log cosine.
I can use log cosines.
You're saying like you drew like something like 5 second triangles and like 2 right triangles. Which stuff I work to?
Okay. So if I just use log cosines down here, let's call this x. So then x squared is going to equal 40 squared plus 40 squared minus 2 times 40 times 40 times the cosine of 120. Okay. So that gets me x squared is 4,800. So x, oops, wrong color. So x ends up being 69.282 feet. Right? Right? Okay. What else is 69.282 feet?
The green.
The green is. Yep. Okay. So now we know that x is 69.282 feet. What can we say? And we said that the purple, black, red triangle is a right triangle. So what can we use to find the red y? What can we use? Even easier. Even easier. Nope. Nope. Pythagorean theorem. Because we've got x, we've got black, and we need red. So if I'm solving for red, I would go y squared equals 40 squared plus 69.282 squared. So that's going to end up being 1600 plus 4800, which is 6400, and the square root of 6400 is 80. No, it's actually 80 exactly.
Well, we rounded the 69.28.
See, that's why we don't round.
Sure.
Yeah.
Like, even there, we're like kind of rounding it a little bit.
Yeah, we rounded, yes. But when I went to use it here, I went back up a step.
Oh, sure.
You know what I mean? And it went right to 4,800 there. Yeah.
Wait, why is pi 3.14? This hexagon literally shows the decimal.
Why is pi? I don't see pi at all.
Yeah, 80 is the right? Each of those is radians.
It's centered around the circle. It's not. It's a hexagon. 60 the equilateral triangles. So each one of those sides of your equilateral triangles is 40. So then you put two of those two together, and you get 40 and 40 gets you the 80. So you had the red right away. Yeah. Okay. So I have a worksheet to hand out to you, and that's all I got for you today.